Yo, 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 here we are looking at section 5.1 and dealing with inverse functions. And the basic way we look at this, so we have f of x is equal to y is what we look at the basic function. We are plugging in an x value and that function will give us the y value. And so in looking at in comparison to that function, its inverse, we have this f to the negative first power. And so this does not mean the reciprocal. So this is another representation of using to the negative first power. So it's not to be confused with that. So what this does mean is that if we take the y value that we got from plugging in the x value to the original function, if we plug in that y value to its inverse, we will get that x value. So simply changing the x and y values is what should be happening with an inverse of its function. Same thing here, this kind of illustrates it. For all of those x values in the original function, it will give us the range of its inverse, simply restating what I said here. Same thing with the range of the original function, the domain will be for that inverse. And see in this next problem, we're just simply doing that. So here's the original function. We have plugged in our x value of negative 3, and we got our y value of 6. That means for the inverse, we should be plugging in 6 and getting negative 3. So all we're doing is switching those values. And you'll see that all through this because that is the definition of inverse functions. Here, we're looking at that. We're looking using composite functions to prove that we have indeed inverse functions. And so when that happens, we're taking the other function and plugging it into the other function. And simplifying, we get x. We do that g of f of x here in red, and we also get x. So that's what happens here. And then, yes, these are inverses of each other because this happened. Whenever we do the composites of two different functions, then they both equal x. So a little review there. Here we're looking at just different ordered pairs, and we're making sure that they're one-to-one. This is when the x is only set up with y values. But since we're dealing with inverse functions, we also have to make sure that the y is not paired up with a duplicate x value because we have to switch those values. So everything looks okay, and as you can see in the answer here, all I'm doing is switching these values. So this y value of 6 becomes the x value. This x value of negative 6 becomes a y value, and we just simply repeat that for each point. Just make sure you put the comma in between there. It can be a little tedious with this. It's very easy stuff, but it can be tedious. And this next problem, here's an example here where the function is one-to-one, but its inverse wouldn't be because we have this y value of 2, and it's paired up with two different values here. So that's why this one is not one-to-one. Here's the first time we're actually solving for our inverse function. And in doing that, we take the original function. So instead of using f of x, we use y, and we just switch those. So the x now becomes the y here, and the y becomes the x. And so then we just solve for y, and that's how we find the inverse function. So we rewrite the original function, we solve for y, and this now represents the inverse function. So that's how I got this x plus 9 over 7. Also visually, we've talked about how we switch the x and the y values, but when we look at it visually, when we look at the graphs of the original function and its inverse, they should be symmetric to y equal to x. And so that's what I have this black line here, and you can see the dotted red line and the blue line. They're symmetric over that, so they're kind of a mirror image of those things. So this is another way to check if we have functions that are inverses. Once again, we're just doing the domain and range of each of these functions. We can see, we have a linear function here, so obviously the domain and range is negative infinity to infinity. And then once we've done that answer, I just switch the answers. All right, so my range becomes the domain of the inverse and vice versa. And we repeat that for the next one. We're just switching our x and y values and solving. Once again, we're looking for the one that goes through or which is symmetric to y equal to x. I didn't draw it on there, but oh well. Here, once again, same thing with the domain and range. And if you're having issues with domain and range, by no means it's just always negative infinity to infinity. That's just not the case, as you'll see in this next problem. Here, here's an instance where we did do that work and we ended up with the same thing. So here's where we have the function is also equal to its inverse, so it's on top of itself here. All right, and so in looking at our domain of the function, we have everything but 0, so negative infinity. So this is where because if we can't plug in 0 to the original function, that's the one that is excluded in the domain. And if we look at our range here, we see this is bottom heavy. So we're reviewing a lot of the same concepts, I think, from chapter 3. So that means that we have a horizontal asymptote through y equal to 0, and that's what affects our range. And then we just switch those, and they just happen to be the same. And we continue this one. This one's a little bit different because we have some constraints here. So we can't have any values less than -7, otherwise we're going to end up with imaginary numbers. And if we have a constraint on the function, we need to have a constraint on our inverse. And so in looking at this, it's like, well, how do I pick between x is less than or equal to 0, and how do I pick x is greater than or equal to 0? And so visually, I think it makes more sense. So if we just graph the inverse, x squared minus 7, as you see here in red, and I have the original function, the square root of 7 plus x here in blue. I have to look at what is the one that is going to be symmetric to y equal to x. And also, if we were to start exchanging x and y values, so we look at this point here, this point is -7, 0. And if I inverse that, it should be 0, -7, which is this point. And if I start doing that, I could see that is including values where I am greater than or equal to 0. So if you need to draw it just to kind of give yourself a better idea of which one to plug in. And then here we can see very clearly that the dotted line, what I have here in red, is the one that is the correct answer. And then looking at the domain here, this is where if we look at, it's much easier to look at here. I start at -7, so this is with a bracket at -7, and then I include all x values here. So that's where my domain is here, and my range, my lowest y value is 0, and I go up forever. And then once I've done that, then I just switch those answers for my inverse. And then in the rest of these, we're just simply solving for our inverse. So we switch our x and y values, and then we solve, and we're done. Same thing here, switch our x and y values, and then solve. And our last one here in green, switch our x and y values and solve. And in these last couple problems, we're just evaluating. So I do the same thing here. I find what is my inverse, and I get the cube root of x. Then it's asking me to plug in 0. I do that, and I get 0. And these next two ones, we're given a function, right? And then we're asked to evaluate its inverse. So I look at this original function. This is telling me, all right, this is my inverse. So this value for x that it wants me to plug in is actually my y value of my original function. So I'm like, all right, what is the x value I plugged in to get -7? So I go over to this graph and I'm like, all right, which point on here has a y value of -7? Bingo! You are the one. What is the x value there? It is -8. Therefore, that means in my inverse, when I plug in -7, I must get -8. So that's kind of the process to run through that. Same thing here. It's asking me to figure out what is my x value of the original function to give me the y value of 5. I find that point. I say, what is the x value here? It is 8. Therefore, that is my solution. Next problem, pretty easy. We're just looking at ordered pairs, and we're just making sure that we have switched the x and y values. I've done so with each of them. If any one of them was not, it would be no, but all of mine have been switched. And this one, very similar to the rest of the problems we've done here. We're just picking the one of the inverses, and it should be symmetric to the y. I'm sorry, y equal to x.